Sorry, sure. All right.
Okay.
Now we are recording.
Yay. Okay, so hello everyone. Like Christina said, I'm Shar. I'm going to tell you a bit about my research discovering fast optical transients with continuous readout mode imaging, which is a very obscure topic within transients, but I think has really exciting implications. And so, like Christina mentioned, we also work together on a project for the upcoming Vera Rubin Observatory astronomical survey, basically. So I'm happy to talk a little bit about that if anyone wants to know about it. Um, and yeah, I'm at the University of Delaware. So an overview of my talk today, which is about half an hour. I'm going to tell you about fast transients. I know that you all already know everything there is to know about Kilonova. So hopefully this will just be like fun. Um, and I'll tell you where my research lies within that. I'll tell you about my data and my analysis methods, and then a little bit on my findings and results. Um, and I just wanted to say that you are totally welcome to interrupt me with questions at any time, and there'll also be time for questions at the end. So just to make sure we're all on the same page about what I mean when I say transients, in case it's anyone's first time here. What I mean is anything in the sky whose brightness changes on human observable timescales. Um, so an example is this supernova that you can see um, happening in this nearby galaxy right here. And through this time lapse, we can see that over like a month, it grows extremely bright and then fades away. And a month is a time scale that we can definitely observe as astronomers. Um, Also, astrophysical transients are often extreme phenomena that can test fundamental physics at a higher energy scale than we could ever see on Earth. Um, so my example for that, if it'll load, is this extremely fun neutron star merger. And I know you all know that as kilonova people because if a kilonova happened too close to Earth, that's it for us. Like the energy levels of these events, um, are so high that we cannot simulate that in a laboratory. And so sometimes the only way that you can concretely test what happens when there's two objects as massive as neutron stars is to observe from this faraway distance through astronomy. Um, and this obviously is an artist's interpretation and not real footage. But it does basically look like that when two neutron stars merge. It's also a realm where it's possible to discover new and entirely unexpected phenomena. You don't need to know what you're looking for when you're searching for transients, because you can just observe what's changing in the sky. And then from there, you can kind of work out what that is. So a couple of my favorite examples of that are from radio astronomy. Jocelyn Bell Burnell was a PhD student when she observed an object that was flickering in the sky every 1.3 seconds, and she actually called it LGM for little green men because she was like, surely there's no astrophysical object that could be doing this. This was in 1967, and it turns out that she had just observed the first pulsar. And in case you think that, well, okay, that happened in the 20th century, but it couldn't possibly happen today, just in 2007, we found the first fast radio burst, which has a distance of 1 million times greater than pulsars. And so it couldn't possibly be a pulsar. And honestly, we still don't really know where fast radio bursts come from, but they're extremely bright and extremely fast. Um, so those are both examples from radio astronomy. For the rest of this presentation, I'm going to focus on optical astronomy. And so I have this really fun map of most of the optical transients that we know about, or at least we knew about in 2024. If anyone has heard of any new ones in 2025, be sure to let me know and I'll update this plot. Um, so the way to read this is we have the brightness. You're astronomers, so you know what magnitude is, hopefully. We have the brightness on the y-axis with brighter objects at the top, and then we have the time scale over which things vary at the bottom. It's a log scale in days, so like 1 day is here right in the middle. And what you'll notice is there's a lot of stuff on this right-hand side of the plot, and this left-hand side of the plot is not very explored. There's a lot of empty space. Um, and that's actually not because there's nothing there. Um, that's actually because it's just really hard to see whatever stuff is there. Now, there may be less stuff there, but there is definitely some stuff. Because if you think about, like, you all have done observations with a telescope, like, there's no way that you could observe, like, less than every second to see, like, what in the sky is changing that fast, unless you do some funky stuff. Um, Here's some of the phenomena that are expected to have second or sub-second variability. Um, so first of all, solar system objects. When we think about the solar system, we usually just think about like these planets that are closest to us, but the solar system actually extends out beyond that into the Kuiper Belt, which are a bunch of like small planet type things like chunks of rock, which many of them were like kicked out of the center of the solar system when it was forming. It's very hard to observe the Kuiper Belt because these objects, they're not stars, they don't emit light. They're so far away that any light reflecting off them doesn't make it back to us. But learning about them means that we can better understand like how the solar system formed, how every solar system forms, um, and what it looks like today. So um, when Kuiper Belt objects pass in front of stars that we're observing, it causes sub-second brightness decreases, and actually it can produce like these diffraction patterns, which are really cool to observe, but hard because obviously the odds that a Kuiper Belt object passes in front of whatever star you're observing at any time are extraordinarily low because they're very small. Um, Another thing that can cause sub-second brightness changes is accretion on compact objects. So this is if you have, for instance, like a star orbiting around a white dwarf or a neutron star or a black hole, and the compact object is accreting matter from its companion, like you can see here. Then there are a lot of different types of very fast brightness changes that you'll observe. These are most often studied in high energy wavelengths and less often studied in optical. But they definitely also vary in optical. There's interesting timescales in cataclysmic variables, which is when it's a white dwarf, from tens of minutes for eclipses, which you can see plotted in optical over here, to seconds for quasi-periodic oscillations, which we don't know exactly what mechanism causes those, but possibly something about like magnetic reconnection, as in the matter that's accreting from one star to the other. Um, Also, optical reprocessing and X-ray binary. So an X-ray binary is when it's a neutron star or a black hole that's accreting matter from the other star. They send out like X-rays like crazy, but they also send out optical wavelengths, and the variability is very fast. You can see this is x-axis is in seconds. Another phenomena that's been hypothesized to vary over these short timescales is blazars, which are black holes, supermassive black holes at the center of other galaxies, where their jets point towards us. And they're constantly accreting matter from the rest of the galaxy, basically. And these are extremely energetic, extremely far away. They can show variability within the night, but they honestly have not been observed on time scales of less than an hour or so. They definitely do have variability on timescales of less than 5 hours, but there are possibility for more rapid variability. And then what would be really cool to find varying in the sub-second regime would be the optical counterpart to fast radio bursts. I mentioned fast radio bursts before. Those were the things that were discovered in 2007. We still don't know where they came from, but we know that they're really bright. They generally come from distances far, far outside of our own galaxy, and they're very fast, just bursts of radio waves. It's possible that there is an optical counterpart that is also varying at that speed. We actually have found one fast radio burst within our galaxy, and it did also have X-rays coming, so multi-wavelength, coming from that source as well. So that's kind of a good sign in terms of more multi-wavelength components, but generally we don't know the source of fast radio bursts, so it's very hard to figure out what's happening there. But that would be an extremely cool thing to discover on the sub-second timescale. So I've alluded to this problem that traditional optical observational methods can't access sub-second timescales. There's some instrumentation that's built specifically for this, but it is rare and expensive. There is a solution, which is that you can change the observing mode on your traditional camera in a couple of ways that can enable observations as fast as millisecond timescales on most cameras. So you can do this with trailing mode and continuous readout mode, which is what I'm going to talk about for the rest of this. So the background of this slide I have here is actually, it is this continuous readout mode data. You'll notice that it does not look like stars like you would expect from an astronomical observation. Instead, it looks like these lines all the way across the screen. And the reason to understand why that happens, let's talk a little bit about how a regular CCD works with this metaphor of the bucket brigade. So essentially, if all of your photons are raindrops, your CCD is going to catch all these raindrops in these little buckets, and then it's going to close the roof and it's going to like scroll all those buckets off to the side so that it can measure how much was caught by each bucket. And generally, when it does that, you don't want anything else to fall in the buckets because that would be confusing. And that would end up, in fact, with streaks instead of with like each bucket being reconstructed to a specific point. But if you operate in continuous readout mode, you can leave the shutter open while that is happening, which means that as the charges are being scrolled off to the side, more photons are entering the CCD, and you end up with this kind of a pattern where at every very small time interval, you get another spatial interval basically on the x-axis until your whole image looks like these streaks. Or I'll go back for a second, until your whole image looks like these streaks instead of looking like the discrete stars that you started off with. So at the beginning of continuous readout mode, you'll get this sort of a pattern where you have streaks that start halfway or so like across your screen, depending on the initial positions of the stars. Eventually, you're kind of just integrating over this axis, so you lose the initial positions of the stars when you're just like taking continuous readout mode after continuous readout mode image. But instead, this x-axis is a time axis instead of a space axis. So we have one space axis and one time axis, and the time axis has millisecond resolution. If we take our star streak and we turn it into a time series, like we just like zoom in on one of those streaks from the previous image, we can like add up the flux and we can see the like fine millisecond resolution and the little wiggles that we get in there. So my group has a bunch of data that was collected in this mode, which, by the way, there's maybe like 5 papers that have used this before. It is not a very common thing to do, but there's a lot left to explore using this. So we collected images from 2022 to 2024 at the Zwicky Transient Facility, which is in California. Looks like that. The data that was transferred to me, which is a subsection of this, is 371 gigabytes, which contains 525 star hours. So that's like 1 star observed for 1 hour. You get multiple stars per image, sampled 600 times a second. Very quickly. This quickly becomes a data problem. And the fields observed at that point, if the galaxy is kind of right here across this axis, we observe some galactic fields and some extragalactic fields. And I analyzed a subset of it. So because this is such a different way to use a camera, there are not pre-made analysis tools to analyze this data. So a lot of what I've been doing in my PhD so far is building tools for this. So I'm going to tell you a little bit about supervised learning to make sure we're all on the same page about how that works, because that's one of the main things that I do with this data. So basically, if you have a brain, which would be a biological neural network or a artificial neural network, you can train it using supervised learning by showing it a bunch of like pictures, like this is grapes. This is grapes. This is an apple. This is an apple. This is an apple. And you show it all of that data along with the association of what that object is. And then when you show it something without a label, so like this picture right here, it has to be able to predict it's grapes. In this example, the grapes and the apples are the training data. And then we also have testing data, which is when you see, okay, if you don't give it a label, will it be able to figure out what this object is? A neural network in general is well, it's basically a bunch of neurons. The purpose of using a neural network is that it can handle very large amounts of data and find subtle and rare patterns, which is exactly what you need to do with kind of big survey data. And it does that by having a bunch of these neurons, which when you give it the example of like, this is grapes, this is apples, it figures out how to associate the label and the thing it's seeing by like training the weights of these neurons. And then you combine a bunch of neurons together and you tell it to minimize a loss function, which we'll get back to later. And that is, in essence, is all a neural network is. I used a convolutional neural network, which is specifically a kind that is good at recognizing patterns in image-like data because it uses a learnable convolutional kernel as a neuron. So for instance, in this picture of like a dog and a cat, like through all of the layers of neurons, it can predict like this is a dog, this is a cat. Here is the structure of my neural network. It classifies not just apples and grapes, but 5 different classes in the context of a square window of pixels around it. So it essentially looks at each of these squares and decides like, what is the central pixel? What is that likely to be? Just like doing that over and over for each part of the image. So I mentioned I don't have just apples, and actually I don't have apples or grapes in my training data. Actually, I have 5 different classes of object that might show up in these continuous readout mode images. So what we would like to find is we would like to find a place where the streak gets a little brighter, a little dimmer. So that would be a brightening transient or a dimming transient. inside of an already existing star or galaxy. It's also very likely to find just a streak, nothing's changing there. It's also likely to find a cosmic ray, which is just a charged particle that hits the CCD, or just background. To build these data sets to show the neural network, you need like quite a lot of data in order for it to figure out how to categorize stuff. I took these classes, the streak, the cosmic ray, and the background, directly from the data. And then for brightening and dimming transients, I took the streaks and I implanted a Gaussian brightening or dimming class or a function. Looked like that, pretty classic Gaussian, to try to be like a general form of any sort of brightening or dimming transient. And if you look at it across like a whole streak, our implanted transients look kind of like this, kind of sharp on a big scale, but smoother on a smaller scale. I varied both the like length, which is to say the duration on the x-axis of the Gaussians, and I also varied the amplitude to see if I could find both like bright and dim transients in the data that I trained the neural network on. And then I trained it. This is what the loss function looked like, which is the thing it's trying to minimize. So looking at it and making sure it's pretty flat on the end is what you want to do there. And it is, so that's good. And then how successful is it at categorizing pixels after all of this training, all of this like data that I fed to it? The answer is that it depends on the amplitude and duration of the transient. Remember, we have anything from like these really short and high transient events to the like long flat ones that to my eye are pretty like indistinguishable from just a streak. And the neural network also thought that was pretty indistinguishable from just a streak. So here I have plotted the duration on the x-axis and the amplitude on the y-axis for all of the transients. And I plotted the dimming and brightening transients on the same plot. So everything above 1 here, or like with a number less than 1, is a dimming transient. And then anything where the number is greater than 1 is a brightening transient, because that's just the amplitude of the Gaussian. And right around 1, you can see the efficiency is purpler, so it is not so good. But anything like above 1.1 or below like 0.9, the neural network detects pretty successfully. So if you remember like the little red square, so far we're only categorizing like pixel by pixel. We have to extend this to categorize like events. So there's a lot of post-processing that comes after this neural network, from aggregating the pixels into like potential transients, rejecting anything that obviously we don't care about, turning it into light curves so that we can analyze that data, quantifying the noise, and then at last like fitting whatever transients we find. So we start off based off the data that I've analyzed, which again is only a subset of all the data we have, with over 6 million pixels classified as belonging to brightening transients and over 4 million classified as belonging to dimming transients. And through steps 1 and 2, which I'm going to fast forward over, we end up with about 67,000 brightening transients and over 200,000 dimming transients, which is still a lot. But not as bad as 6 million in terms of like stuff we have to look at. And then we extract these light curves. You can see that like sometimes the streaks are a little wiggly. So when we wanted to capture like all of the light from the streak and not just like use the like center pixel here when we determine like what the light curve of these events are. So we have like about 5 pixels per time step, and we let it vary depending on like if it wiggles up or down, so that instead of this like dramatic dip that is not an actual physical transient, everything's a little more contained. Um, there's two main types of noise in this data. There's the shot noise, which is just from like the random processes that lead to the photons entering the CCD. And then there's also the standard deviation based off of like what the data actually looks like. And this is what we use for our signal to noise ratio definition, is like how much the pixels on either side of the like transient detections vary. And when I plotted the signal to noise ratio, I got like this histogram, which like for all of my data scientists out there, like this is the best ever histogram that you could see. Like these are two very distinct classes. And what it turned out to be was that anything with a signal to noise ratio of greater than 25 turned out to be a moving object, because the streak was kind of going diagonally across the image, which means that the position of the object is changing in time. So obviously, like this is a giant signal to noise ratio, because this is like thousands and thousands of times bigger than the baseline. But unfortunately, we're not looking for moving objects. So we rule out all of those. And then we're left with some decent looking transients, and we fit a Gaussian to them just to kind of get a sense for what they look like. So I'm going to show you some of the ones that we have found and some of their parameters. Here's some dimming transient candidates. They have a variety of shapes in their light curve for the actual dimming, but they all have a signal to noise ratio of bigger than 9, which is pretty significant. One thing to note is this is a local signal to noise ratio, because it's only about 100 pixels on either side. So for instance, in this one, if we look at the whole like 10-second exposure, we can see that there's other variations that are also as dramatic as this one, which could imply that this is some sort of like variable as opposed to a transient, like something that regularly repeats, or that there's just some kind of regular noise happening in this transient. Of the science cases that we've brainstormed so far, so like occultation by a Kuiper Belt object, or a cataclysmic variable eclipse, all of these are too fast to be that specific kind of dimming. So further study is required to figure out exactly what all of these dips are, and whether they're even real, because surely most of our like 60,000 transient candidates are not real. But because no one's ever like looked at this stuff before, it's not apparent like what is just some strange sort of noise and like what is an entirely new object that we've never heard of before. For the brightening transient candidates, pretty similar story. They have a variety of shapes. They're pretty significant, but quite short. And all of these are, oops, sorry. All of these, I think stars are actually stars and not galaxies. So we're probably looking for a galactic source for these types of transients, as best as I can tell. But again, I like literally just found these, so I am not claiming to have actually discovered anything. More, I'm claiming that like it is possible with this pipeline to find stuff if stuff exists, and we'll do a bunch more research into whether these are actually anything, and if so, what. Um, so that's like a sneak peek of my conclusion, um, where I want to emphasize um, that fast optical transients are really cool and important because astronomers have barely explored what in the sky varies in less than a day. Less than a day, mind you, much less like less than a second. Um, Transients are often extreme high energy phenomena that test fundamental physics. Um, and surveying wide areas of the sky for like your maximum discovery potential to find subsecond transients is possible using continuous readout mode imaging. Um, and then I have built a pipeline that retrieves sub-second astrophysical transients in continuous readout mode data and retrieves several candidate events for further study, such as this one. Um, and my next step is we're replacing the convolutional neural network with a transformer neural network that will be able to categorize the pixels based off the whole streak and not just the parts of it that are closest. So I can talk more about that if you want. But that's my next step in addition to investigating the events we found already. So um, I will I would love to take questions. I'll stop sharing, but then I can share again if anyone has questions about anything specific.
Awesome presentation, Shar. Thank you.
Thank you.
I really didn't know that was how continuous readout mode behaved. That was a really cool figure that you had with the stars moving across the screen. Very, very illuminating. So we got two questions, one from Eric Bowen, one from Anand, and then the third from Heinz. So Eric Bowen says, do you deal in some way with atmospheric scintillation seen?
Yeah. Um, I think, and similarly to turbulence, I think the time scales for those are a bit bigger than millisecond. Um, And ooh, there's so many good questions. This is great. Um, and so those are going to cause like the whole streak to like move um eventually, but they're not going to impact the like every 1 millisecond time scale. So that's like when I let like the center of the aperture basically move based off of like where the star is. That should account for that to my best understanding.
And for clarity's sake, this will probably go on YouTube, and other people might have questions. What is atmospheric scintillation?
Does someone who's more of an astronomer than me want to answer that?
Ooh, no takers.
No
Interesting.
takers. Well, I don't want to put an incorrect explanation on YouTube. So if you're on YouTube, please Google this.
It's caused by the random distortion of light as it passes through the Earth's turbulent atmosphere. All right, so I assumed that's what it was. I thought there would be something more exact to it, but yeah, so it's just how the atmosphere perturbs the photons coming through.
Yeah. Um,
I just is our Nas question, is that the same? Do you take turbulence into account?
yeah. So right now, not really. We don't really have a good way to model it, and we're hoping that the neural network will be able to just differentiate between like regular turbulence because we like give it examples of like what all of this like all of the streaks normally look like with no transients, so including um the turbulence versus like this is what it looks like with a transient in it in addition to turbulence. um and now after finding stuff, now we have to go back and figure out if it's turbulence or not. So like, yes, that's rapidly becoming relevant.
Fine, you had a question?
I think Heinz put their question in the chat. Um,
Okay.
yeah, so actually one of someone working with us is looking. So, okay, for context, the question is, have you tried this on the optical pulses of the crab pulsar, um, which is about at 30 hertz? Um, would you observe such an object with a slit covering the CCD to reduce the noise? So, one of our collaborators is looking at that. Um, we don't have those results back yet, but yes, we're going to do that. You might do that with a slit covering the CCD. I'm not sure on that one. Um, and then there's some more questions in this chat, so I'm just going to keep scrolling up. Um,
Michael Freeberg said, have you used CMOS detectors in continuous readout mode?
no, I think this is CCD specific. Although if anyone has used CMOs, like feel free to tell me if that is possible.
Dennis Schmackay says, problem with CMOS, the data throughput, say 20 megapixel at several kilohertz frame rate. Oop, that moved. It's just awful to manage at its interface.
Yeah. Yeah, you could use drift scan. That would be a cool thing to try.
Yeah, Theory said earlier, yes, CMOS APS matrix to propose use such mode or event-based CMOS arrays.
Yeah. I think that CMOs also are generally a narrower field of view. So if you're going for like discovering new things, um, they may not be as good of a choice. Um,
Another asked, oh, sorry, go ahead.
oh no, you're good. You can read it.
Another asked, are you aware of the Laser Study project?
Yeah. Um, I have heard of the Laser Study project. I have not talked to them yet. But it does seem like they are looking for like millisecond and faster like laser bursts. Um, so it would be a fun collaboration at some point to compare what we're doing.
That was a topic at the Transition Space Conference last week, which was how we are going to collaborate, how large surveys are going to collaborate together for
Mhm.
targeted opportunity events, and how they're going to collaborate in general with all this information that's coming in now that Roman, Rubin, JWST, Hubble are all going to be in the sky together or looking
Mhm.
at the sky together.
Yeah.
So I hope that we have more of these conferences where we can actually see some output of that. And I think that with once all these are in the sky together, I think that'll happen very quickly. I think people are more hesitant now since there aren't since Rubin isn't completely greenlit or isn't completely lit up yet, and it's just a WST up there, and we're still waiting for Roman to launch 2027.
Mhm.
And then there's all the other ones from international launching in 2030 to 2035 too. So we'll see what
Yeah.
happens over the next decade.
Yeah.
There
It's
was two more comments. Sorry, go ahead.
Oh no, it's just a great time in like multi-messenger astronomy and just like multi-wavelength astronomy, really astronomy in general. Like we're if we can collaborate, we'll find so much cool stuff.
I agree. It'd be nice, detect something uh, with Vera Rubin, observe with JWST, and localize with Roman, get some deeper analysis there.
Yeah.
So Anand makes a comment saying you could use drift scan, which would allow CMOS usage, I would guess. And Denise Marquez says CMOS are very bad at charge transfer. CCD remains a good guy for drift scan like modes, like the Gaia ones. I don't know if you had read those.
Yeah. But yes, good points. Thank you all.
Any other questions? Oh, I'm not asked another. How far down in magnitude can you go with the Palomar Schmidt?
This is what I'm trying to quantify right now, because you wouldn't believe how hard it is to actually figure out what stars are which when you're in continuous readout mode. Um, I think that so I'll have a better answer for you in like 1 to 2 weeks. But confidently, we can go pretty bright, pretty bright. Not very dim, but confidently like 11th, 12th magnitude in G. I have G, I, and R. Um, like some things a little dimmer, but then obviously the signal to noise ratio is not as good. Um, So I'd be more hesitant to claim I detected something at like 14th magnitude.
What would you say would be so if you have to choose another telescope to work alongside with to help support your observations, what would that look like?
Hmm, that's a good question because I think like ZTF really is a survey telescope. Um, so we like could find stuff um over a very big area, but then like we would certainly need to follow up with something that could do like more localized, like more detail. Um, I yeah, if you have suggestions, um, I don't anything.
Because if you're only getting down to 11 or 12 magnitudes, you need something that could be within that error to kind
Hmm.
of see where if you're not comparing, or at least something stronger at least. I don't know.
Yeah,
I think that's something that would be a cool answer for when we have all these active surveys going on.
yeah. And
Uh,
then mhm.
Go ahead.
Yeah, Arno had a question about overlapping streaks. Yeah, since you're integrating across like the entire X spatial dimension, stars do overlap. And the way that you can reconstruct that, and so for now at this stage in my analysis, I'm generally just only considering stars that don't overlap, because it is more complicated if they do, but you can reconstruct um, whether an overlapping star uh, event is related to the stars versus like related to the fact that there's just like two of them and maybe they're like wiggling because any wiggle is going to appear multiple times in the image at different positions based off of like where the initial positions of the stars are. Um, so that is possible, and we haven't done it yet.
Fascinating. Heinz asked another question. Are all the SAT constellations a problem for this kind of research, eclipses and reflections?
Yeah. Um, Satellite. Yeah. They are not, they are not as big of a problem as they will be for like the LSST. Um, because I can just like say if it's like moving, then I throw it out. It's a pretty clear criteria for that. And because I'm already looking at things that are bright, like satellites being too bright and bothering the CCD is um, not as much of an issue for this one. But obviously, also, if there's like a transient event that occurs like in the path of or right next to a satellite, then there's just like no chance of seeing it. So more satellites is worse, certainly.
Okay, satellite constellations make more sense. I wasn't sure what an SAT constellation was. All right, any more questions? Any other
Yes,
comments, Shar?
yes,
Oh,
Christina, I would like to share with you maybe a technology from a French company. The name is Prophecy. I don't know if I'm able to share my screen. I just want to show you the website because it's a small startup. I had the opportunity to work with them a few years ago, and they propose, a CMOS arrays, and in each pixel you have a threshold comparator, and so in each pixel, in parallel, you have the ability to detect if the signal is rising or dimming at once, and you read only the pixel which is changing. And here you have I have maybe no time to explain how it works, but you see that compared to a standard pixel array where you are obliged to read all the pixels to get a picture, here you read only the pixel where you see a change in the level. And this technology is today in mass production in Sony.
Cool.
If this could be helpful for you, of course, we have to design a very specific telescope. But I have the chance in the past to use such a device, and we show that, for instance, we were able in a landscape to detect, for instance, a laser modulation, a spot, and we detect the laser modulation with megahertz bandwidth. It's it's amazing, and I'm always dream to use such array in front of the sky.
Yeah, that is awesome. I would love a telescope that did that.
Katie, would you like to do like a short blurb on this at the telecon next week? This seems very interesting.
Yes, okay. Why not?
Like 15-minute presentation on it?
Okay.
All right, sounds good. I'll be excited to hear more about Shar if you'd like to come next week, same time, if you want to hear more about what Jerry has to say.
That would be very
Okay.
cool.
All right, wonderful. Oh, and we had another interaction on the chat. So Eric Rowan says, it might be interesting for asteroid occultations, I guess, too, since the time of the occultation is usually very short. Shar responded, yes, about 0.2 seconds for Kuiper Belt objects.
Closer art a bit longer or whatever, but yeah.
Thank you so much, Shar. This was truly interesting, truly wonderful. It was nice to see a little more about your research outside of what we do together with Bear Rubin.
Yep.
And I learned a lot of new things today, which is really always a nice day for that.
Totally. And everyone, please feel free to reach out if you have more ideas of what I can do with this, since it is all quite new. I really appreciated all of your questions. And Christina can give you my contact information again if you like.
Yeah, absolutely. And if you guys are interested in more of this too, you can also put in the topic request form, because I would be more than happy to find someone who can expand on this for us, or if Shar knows somebody, or Shar would like to give a second presentation, of course, to fill out these questions. And I will be posting these questions that you guys have within the Slack, so to answer them. All right. Well, I'll see you guys next Tuesday at the same time. Thank you so much, Shar. Have a great day.
Thanks for having me.